Hi, welcome to VC Video 10.48 Part 1, Introduction to Polar Equations.
On to polar. Okay, so just a reminder, with rectangular equations, you have y as a function of x, you have an x-axis, a y-axis, you have ordered pairs xy. Even with parametric equations, you have x as a function of t, y as a function of t, but you're still graphing it on an xy axis. You're still graphing ordered pairs xy. It's just that and when t equals 3, for example, x may be 0 and y may be 1. But basically you have xy, which means you're going left, right for the first coordinate, up, down for the second. Polar equations is a whole different world, and what you have now is r as a function of theta. So here is some graph paper. People are loud. I'm at school. Anyways, so the origin is now called the pole. The x-axis is no longer called the x-axis, it's called the polar axis. The y-axis is called the pi over 2 axis. And instead of going right, left, and up, down, we are going to go right, left, but we're not going to go vertically up and down. What we're going to do is follow along the circumference of a circle. So, for example, you have a circle of circumference 1, radius 1, radius 2, radius 3, radius 4, etc. And then, for example, if I go to r equals 2, my first coordinate is going to be r, which is the radius of that circle, and my second coordinate will be theta, which is how many degrees or radians I'm traveling along. So if I look at this in degrees, I'm going to the right 2, and then along that circle's circumference, I'm traveling 45 degrees. The thing about polar coordinates is they are not unique. If you go back to an xy situation, if I was to pick a point here, 4, 2, the only name for that point is 4, 2. But in this case, I could call this 2, 45 degrees. I could say it's 2, negative 315 degrees. I could say it's negative 2, 225 degrees, etc., etc., etc. So I could go right 2 and left 2 and go basically that angle plus or minus any complete revolution, which is plus or minus 360 degrees, and I'll end up right back there. Okay, so very important that you know it's r comma theta. Do not put theta comma r. It's r comma theta, kind of in alphabetical order, r, s, t, t for theta. So again, in the rectangular system, we go up and down, right, left, up, down. There's a one-to-one correspondence between the points on a rectangular coordinate system and their coordinates. But a point on a polar plane has an infinite number of possible polar coordinates. So as we saw, again, I could take this point right here, and I could say, okay, well, I go to the right 3, and then I travel 60 degrees counterclockwise. Of course, I could say that I went 3, and then I might go this way around, clockwise, negative 300 degrees. I could go negative 3, which would bring me here, and then do negative 120 degrees. Or I could do negative 3 and go 240 degrees, which would bring me right back up here. So, again, here, these are the radii of the different circles, and this is 15 degrees, 30, 45, 60, 75, and 90 degrees. That's called the pi over 2 axis. Now, as far as how to get there for a point, 360, so the idea is this. You move 3 to the right, and then you went 60 degrees. Other ways to get to that point are either going to go 3 to the right or 3 to the left, so there's 3 and negative 3. And then what you're going to do is either go the 60 degrees and then go from there a complete revolution or 2 complete revolutions, etc., or 3 complete revolutions in either direction. So there's your 60 degrees plus k times 360, where k is any integer. The other way is to go left 3. So if you go left 3, then what you have is negative 120, which is basically, if you take 180 minus 60, you get 120 and put a negative in front of it, and then you can add multiples of 360 to that. Okay? So it is a very different way of graphing. They're going to first have you convert polar coordinates r theta into rectangular coordinates xy, and then going backwards from rectangular coordinates to polar coordinates. So what we need is a relationship between the x, the y, the r, and the theta. So if I was to draw a portion of a quarter of this circle right here, so it has a radius of r, which is the green to here, and then I travel, say, theta radians along that circle. So my theta is actually this angle right here. If from that point I was to drop a perpendicular, let me actually just fix this a teeny bit, because the x would actually stop right here. I don't want you to think it goes any further. So this goes to here and stops there. Okay, that's where my x stops, right there. So I could call it the point xy. So the object of the game now is, what is the relationship between xy, r, and theta? Well, what happens is that if you look at this graph, the sine of theta is y over r, right? Opposite over hypotenuse. Well, if I isolate the y, that gives me y equals r sine theta. So if you are given r and theta, you can find y by taking r times the sine of theta. Same thing happens with cosine. If I look at cosine of theta, it's adjacent leg over hypotenuse, which is x over r. If I do a cross product, I get x equals r cos theta. So again, if I have r and theta, I have a way of getting x and y. So given the polar coordinates, you will be able to find the rectangular coordinates. Now, in the opposite direction, if I'm given the rectangular coordinates xy and I want the polar coordinates r theta, if you look at the relationship between x, y, and r, of course, it's the Pythagorean theorem, and it's x squared plus y squared equals r squared. So if you were given x and y, the r is plus or minus the square root of x squared plus y squared. Now, the next one is a little tricky, and that's why I'm always going to tell you to graph your polar point before you make this decision, okay? The next one is the relationship between x, y, and theta. Now, I'm sure you can all see that the tan of theta is y over x. But what happens is, you might think, oh, so theta is the inverse tan of y over x, which is why I left that part in red. But the problem is that, by definition, the inverse tan of y over x, remember, inverse tan, the answer will be between negative 90 degrees and 90 degrees, or negative pi over 2 and pi over 2. And of course, our angles might go into the second, third, fourth quadrant. You never know. If they go into the second or third quadrant, obviously an angle between negative 90 and 90 is never going to get to those quadrants. So I like to look at it this way. Not that theta equals the inverse tan of y over x, but that the reference angle for theta equals the absolute value of the inverse tan of y over x. Okay? So, just to recap, if you're given r and theta and you want to find x and y, x is r cos theta, y is r sine theta. If you're given x and y and you want to find r and theta, r is plus or minus the square root of x squared plus y squared. And the reference angle for theta is the absolute value of the inverse tan of y over x. I would definitely draw the point to see which quadrant to help you get the actual value of theta. So here's an example. If they give you the polar point and they want you to change it to rectangular coordinates, we have x, remember, is r cos theta, and y is r sine theta. So I'm going to plug that in. I have negative 4 cos theta, negative 4 sine theta. Of course, the cosine of 60 is the same as the sine of 30, which is a half. That gives negative 2. And the sine of 60 is root 3 over 2. So that gives negative 2 root 3. So the rectangular coordinates that are equivalent to negative 460 are right there. And by the way, there's 1, 2, 3, 4, negative 60. And it makes sense that the two coordinates should be negative because it's in the third quadrant. Now we're going to convert an xy into an r theta. So x is negative 1, y is negative 3. So remember, r squared is x squared plus y squared. So r is plus or minus the square root of x squared plus y squared, which is plus or minus the square root of negative 1 squared plus negative root 3 squared, which will give the square root plus or minus 2 in the end. Okay, so r is plus or minus 2. Remember, there's multiple different versions. There's an infinite number of ways you can name a polar point. So that's why you have a choice of 2 or negative 2. The reference angle for theta is the absolute value of the inverse tan of y over x. So I would graph this point to see where it is. You can see that -1, -√3 is obviously in the third quadrant. And if you do the inverse tan of y over x, what you'll get is you'll get 60 degrees. Well, obviously, I mean, if you decide to write the point as +2 comma, well, it's obviously not +2 comma 60 degrees. Now, as it turns out, it is -2 comma 60 degrees. That actually works out quite nicely. Okay, so -260 would work, but if you wanted 2, which means you're moving to the right, realize that the reference angle for your angle is 60 degrees.